In this video, we're going to begin to learn about bonding. So we need to recall the idea of valence electrons. Valence electrons are the outer shell electrons, or the electrons in the outer energy level, and this is really what determines the chemical properties of an atom, so how they will behave and how they will interact with other atoms around them. Valence shell electrons are only ever S and P electrons. Remember, that's because the S and P's will fill, and then before we go to the D of that same shell, we'll go up to the S of the next shell. So the S and P are always the outer valence electrons. So they're in the highest occupied energy level. The core electrons are all the ones below, and they're not quite as important. So we learned how to draw dot diagrams, and we kind of use these Lewis dot diagrams in order to help us determine what kind of ions are going to be formed. So metals have very few valence electrons, usually less than 3. So calcium is an example. Remember, we can know the number of valence electrons based on the column on the periodic table. So calcium is in column 2. It has 2 valence electrons. Okay. Now, metals tend to lose their valence electrons because they have so few of them. So if calcium is to lose 2 electrons, then it will form a positive cation and have a +2 charge. When we see an ion written like this, we actually rename it. Instead of a calcium atom, we say that it is a calcium ion. And we don't show any dots for the cation. Now, some elements on the periodic table fall into the transition metal area. The transition metal area, remember, isn't in a column where we can determine valence electrons. So if we look at the electron configuration for scandium, scandium is number 21. So it has 4s2 and then 3d1. So it has 2 electrons in its outermost shell, in the 4th shell, but then it sort of has this 1 d electron hanging out. Okay, so any transition metal we say they have variable charges or oxidation numbers, which I'll explain here in a second, and that is because they tend to lose different amounts of electrons. So scandium might lose 2 electrons from its S2, or it might lose all 3. So we can have a scandium ion that is scandium +2 or scandium +3. And I know these dot structures aren't exactly correct. So when we name those, we have to use a Roman numeral to tell specifically which ion we're talking about, because it could have a different charge. So we say scandium 2 ion or a scandium 3 ion. Now, anions, and again, this dot structure isn't exactly like how I taught you, but I put the dots over there so we could sort of see it, have this visual for an example. Okay, so anions are formed when nonmetals gain electrons, and that's usually an anion is formed because a nonmetal has more than 5 electrons, and again, they're trying to achieve an s and p orbital that are full, so they're going to gain electrons. So they gain electrons to fill their outer shell, and so when you pick up 3 negative electrons, you then have a -3 charge. Now, for an anion, we rename it as well, and what we do is we take the root of the name and we change the ending to IDE. So instead of phosphorus, we have phosphide ion. And, you know, at the beginning when we're just learning, we can show the dots, but we'll stop using the dots after a little while. Okay? So really what an atom is trying to achieve is a stable electron configuration, or something like a noble gas. Okay? So they're going to try and pick up electrons or lose electrons until their S and P of their outer shell is full. Okay? So again, this is argon. It's a noble gas. It has 2s and 6p electrons. So we're really shooting for 8 valence electrons, and when you have 8 valence electrons, you have a pretty stable conformation. Okay, so because bonding sort of occurs in order to achieve that 8 electron configuration or situation, we call it the octet rule. So if we look on the periodic table, we have columns 1 and 2 and 3 here, and those are all metals, so they tend to lose electrons, so they get a positive charge. So one valence electron will lose that valence electron, have a +1 charge. Column 2 has 2 valence electrons, it'll lose 2, have a +2 charge. Again, the transition metals can have different numbers that we need to use a Roman numeral in the name. Then we have the third column, so it's a +3. The fourth column is a mixture of metals and non-metals, so we have sort of a plus or -4 situation. Then in the third column, it's going to pick up 3 electrons and become negative. In the sixth column, it'll pick up 2 electrons and have a -2. In the seventh, it'll pick up 1 electron and have a -1. These numbers right here, I would write those on the periodic table in your reference packet. These are the oxidation numbers, we call them. Alright, so an ionic bond is when an anion and a cation are held together because they have opposite charges. So opposites attract, plus and minus charges attract. We call an ionic compound a salt. It's sort of a generic name. And the simplest ratio of elements and how they combine an ionic compound is called a formula unit, abbreviated FU. The bond is formed through the transfer of electrons. So actually, electrons are actually lost or gained by one atom or the other, and then they are attracted because of that transfer of electrons. And again, the whole reason why they're transferring is to achieve that stable noble gas configuration and follow the octet rule. Okay? So again, ionic compounds are called salts. They're made between a cation and an anion. We know cations are metals and anions are nonmetals. So an ionic compound is actually the combination of a metal and a nonmetal. Alright, so let's look at an example. I know we looked at sodium chloride already. So we have sodium. It tends to lose 1 electron from its outer shell. Chlorine needs 1 to have 8. So again, they exchange electrons. The nonmetal chlorine gains, the sodium loses. They have opposite charges and therefore are attracted to one another in an ionic bond. Okay, I'm going to skip that slide because I think we've sort of covered that. Alright, so that's sort of an easy one-to-one exchange. Here's an example that's a little bit more complicated. So you have calcium that has 2 outer shell electrons and phosphorus that has 5. So calcium has 2 to get rid of, and phosphorus needs 3. So what ends up happening is we account for all of the electrons and we try to achieve this stable noble gas configuration. So what will happen is one calcium will come along and he'll give 2 electrons to phosphorus and become positively charged, a +2. Then if we bring along another calcium, it can give up 1 electron to this phosphorus and form a phosphide ion. And then we bring in another calcium or another phosphorus. He takes that electron from calcium. And then a third calcium will donate his 2 electrons and we have another phosphide ion. So the ratio at which calcium and phosphorus are going to combine is a 3:2 ratio. And we write that as an ionic formula. This is the formula unit. 3 calciums, so Ca3 to 1 or to 2 phosphides, P2. Okay, this is the chemical formula. We're going to learn about how to write the chemical formula, the numbers, and what they mean in the next lecture. Okay, so the last thing I want to talk about is about properties of ionic compounds. Ionic compounds are crystalline solids. So table salt is one of the most commonly used ionic compounds. So when you want to think about an ionic compound, think about table salt and what you know about it, and that's sort of a good way to remember the properties of ionic compounds. So it's a crystalline solid. The ions are very strongly bonded together. It is a really extremely strong bond, and it has a very rigid structure. Okay, it has an extremely high melting point. To melt table salt, you would need like to hold a blowtorch on it for a while. It's over 1,000 degrees Celsius. So they have extremely high melting points. Okay. And lastly, they conduct electricity. Conducting electricity means that you allow charge to move from one direction to another. So when you have a solid ionic compound, like some table salt, the ions are locked in place. They can't move from one place to another. So when they're solid, we actually say they're insulators. They do not conduct electricity. However, if we melt them, then they become liquid and they can flow. So when they are melted, they conduct electricity because the ions or the charged parts can flow from one side to another. Okay. Again, though, it takes a really high temperature to melt ionic compounds. Now, the other way that we can that they can help us to conduct electricity is when we dissolve them in water. So when we dissolve them in water, essentially what happens is we say the ions dissociate. So the sodium and chlorine, they would separate, and because they're in a solution and they're in water, they can flow from one place to another. So that would be the movement of electricity or charge from one place to another. So ionic compounds can conduct electricity, but only when they are either melted or dissolved in a liquid. Okay, so here you can see we have sodium chloride, so it's table salt dissolved in this water, and because the ions can move freely in the water, then we can conduct electricity.